Hello there! Now we have a problem about light coming in from a window. A window consists of a rectangular piece of clear glass with a semicircular piece of colored glass on top. The colored glass transmits only 1/2 as much light per unit area as the clear glass. If the distance from the top to the bottom across both the rectangle and the semicircle is 2 meters, and the window may be no more than 1.5 meters wide, find the dimensions of the rectangular portion of the window that lets through the most light. So this problem might seem a lot different from what we're used to. No fear, we just get out our markers and we draw a picture. Draw a picture. All right, so let's see what we have here. We're going to have a rectangular piece of glass, and that's the clear part, and then we're going to have a shaded semicircle. There we go. And so to show that shaded, I'll shade it with my purple pen here. And we know some more facts about this. We know that the maximum width is 1.5 meters. There we go, that's the maximum width. And we know the height is always equal to 2 meters. It might be helpful also to label some more things. So let's call this Y. We'll call this R. And we'll call this distance X. Once we have our picture, we got to determine your goal. All right, so let's look at the picture again. Remember, we're talking about the amount of light that comes in, and the light has to do with the area. So the area of this semicircular region is, well, it's going to be pi r squared all over 2, because it's half a circle. And only half as much light comes through, so the amount of light is going to be 1/2 times pi r squared all over 2, plus now the area of the rectangle, which is x times y, and we'll call this L for light. Now we find constraints. All right, so some constraints. Well, one constraint is that y plus r has to be equal to 2. That is a constraint. Another constraint is that 2r is equal to x. Another constraint is that r is greater than 0, x is greater than 0, and it's less than 1.5. I guess we can say r is going to be less than 1.5 divided by 2, which is 0.75. And we know y is greater than 0. So these are all constraints for our. And now, solve for a single variable. All right, so look at our picture here. We have lots of variables floating around, and if we want to solve for one, well, let's collect our information together. And I'm sorry, but I want to do what's ever easiest. So I want to do, I have y plus, look, I have 2r equals x. So I want to replace x with 2r. And I have y equals, y plus r equals 2. So I can say y equals 2 minus r. And now I can say L is equal to 1/2 pi r squared over 2 plus 2r times 2 minus r. And while we're at it, why don't we simplify this down and make it a little bit easier to take the derivative of it, because that's what we're going to do later anyhow. So L is equal to, let's see, pi over 4 r squared plus 4r minus 2r squared. That seems good enough to me. It's not a calculus class unless you use calculus to find the extreme values. All right, so what we're going to do is we're going to take our function L and we're going to differentiate it. So let's go ahead and work over here. So I have, let's see, L prime is equal to pi over 2 times r plus 4 minus 4r. There we go. Okay, so now I can collect my r terms. L prime is equal to pi over 2 minus 4 times r plus 4. And if I want to see where a possible critical point is, I can see where the derivative is undefined, it never happens, or where the derivative equals 0. So I could write 0 is equal to pi over 2 minus 4r plus 4. So negative 4 all over pi over 2 minus 4 is equal to r. But here, something interesting happens. We find out that r is around 1.6. If we go back and we think about our constraints for r, the largest r could be was 0.75. This is impossible. We can't have this. So we need to go back to the drawing board. We need to go back to our derivative, maybe at this step right here, and think about what's going on. If r is less than 1.6, what's going on with the derivative? Well, let's see. Pi over 2, that's about 1.5. Minus 4, so this is some negative number. And if r is between, say, 0 and 1.6, then this whole thing is positive, which means that increasing r increases the light. And this will happen up until r is equal to 0.75, which is the maximum value for r. And so that tells you that x should equal 1.5 meters and y should be 1.25 meters. And that's our final answer. So here we see a different type of optimization problem. Here we see one where the maximum value is right at the constraints. This happens sometimes. We got to see it. We got to do these problems. All right, time to do some more math.